Start recording. Right. Now, I guess last Tuesday we discussed about what will happen to these low mass stars at the end, right? So today we will discuss what will happen to high mass stars when you have a stars where you have these higher masses, which means these are specifically stars where you have in this top left hand corner on the main sequence in your HR diagram, right? Now, if I bring this stellar life cycle diagram again, so this is so this is the part actually I am trying to discuss this week for massive stars. What will happen, right? Until the supergiant phase, it will looks like the process will be similar until you have this carbon at the central region of the star. But for the low mass stars, remember what has happened was, so their mass is not enough to create enough central temperature to make heavy materials other than carbon and oxygen, right? Because of that, their star formation process will stop at that particular point, and then you will have a white dwarf star at the end. So that's what has happened to these low mass stars. But the story for the high mass stars is a bit different, uh, because that these high mass stars have enough gravitational power so that they can have these higher temperatures at the central region of the star, which will help to make these heavy materials other than carbon as well, right? So that's why I have mentioned here that the high mass stars are able to burn their carbon cores, and this requires uh, a higher temperature, around 600 million degrees of Kelvin, right? So you have to provide this much of temperature to make these heavier elements other than carbon, right? Now, the stars which are greater than 8 solar mass will not end up as white dwarfs because they will be able to provide these higher temperatures so that this carbon can be fused into heavier elements, right? So that's what will happen. So these higher mass stars will be able to make these heavy elements such as neon, oxygen, magnesium, and silicon, right? So, you know, these are heavy metals, right? And this leads to an onion skin layer of materials in the core, and the temperature increases with the depth in the star, and each successive stage occurs faster than the previous one. And also these supergiant stars will also undergo a substantial mass loss, right, during this reaction. So they will lose their mass. Now, what this onion skin layer means is something like this. Now, this process of making heavier elements is somewhat similar to what we have been discussing up to now, because when you remember that initially you had hydrogen at the central region of the star, and then you have when hydrogen burns into helium, you had helium ash at the central region, and then helium burns, and then you had carbon at the central region, right? So that's what has happened up to now. So once you have carbon, then there are shells outside And on these different layers, you have these lighter materials, right? For example, once you have the carbon at the central region, you had helium shell next, and then there was a hydrogen shell outside, right? In similar way, when carbon, when the at the central region, when carbon start to burn, it will make the next heavier element, but at the same time, then you will have a carbon shell outside. Like that, this will continue step by step until it makes the heaviest possible element that it can make, right? So that is what will happen. And because of that, uh, as you see in this diagram, you will see there are different layers of materials or metals now in the star, right? In the central region, you will have the heaviest material, which is iron, and then you have a silicon shell after that, and then oxygen shell, neon shell, carbon, helium, and from the outside, the outer layer is like a hydrogen fusing shell, right? So that is how the star looks like at this particular region, and this is very specifically for high mass stars, right? Right. Now that is the process for high mass stars. Now these high mass stars, as you see here in the central region, you will have an iron core at the end, and all these the high mass stars, they will end up with this iron in their cores, right? Now iron is a very special material, that is because it is unable to produce energy via fusion, right? Now, if you have done a little bit of nuclear physics, and if you remember this binding curve for the nuclear binding curve, it has one of these. So the shape of the binding curve is actually something. It goes like this, and then there is a maximum, and then goes down like that. So this highest point is where you have iron, right? So that's why inside the stars also the iron is the heaviest element, because it cannot fuse again to make another new element theoretically, right? So that is why you have iron at the center, right? All the other elements you can fuse, and fuse make heavier elements, but for the iron you cannot do that. So this is why you have iron at the central region of these heavy stars, right? And so once you have the star at this particular point, again the internal nuclear reactions or fusion reactions will stop after you have iron, right? So then what will happen is gravity takes over in the core, so that the star will further collapse again, right? So this is the same procedure that we discussed for white dwarf stars as well, right? So once you do not have any nuclear fusion reactions going on the central region of the star, so there is nothing to produce this pressure at the central region to balance the gravity, and because of that, the gravity takes the lead and will continue to collapse the star, because gravity is an attractive force. Now it will collapse the whole star, right? Now because of this huge mass and very high temperatures involved in this particular process, this process will become more and more violent compared to these low mass stars, right? Remember that we are talking about huge masses now and very high temperatures. So just think about a situation like that. The high temperature means that these are millions of degrees of Kelvins, right? So that's why the process is very violent at this point. Now, at the central region, actually what will happen here is the star's core will implode. So implode means that you have a like an explosion towards the inner region, right? Because this is because of this very high temperature and higher masses involved in this process, right? Now, At the end, once the gravity contracts everything, the pressure will again increase, right? And the pressure will become so the so once the pressure increases, the temperature increases, and the temperature will become up to 10 billion kelvins at the end of this process, right? Now, when you have this much of temperature, so there is something specific that can happen. That is, this kind of temperature will create photons with extremely high energies. Now, these high energy photons can even break up these heavy elements in the core. So, what will happen is, due to these very high energy photons created as a result of these 10 billions of Kelvin temperature, uh, the heavy elements will break up, and then you will have protons, neutrons, and electrons in this core region, right? And this process, or this whole process, is what we called as photodisintegration, right? So this is a specific name. Right? So if I explain the same thing again, what this means is, what photodisintegration means is, once you have this very high temperature like 10 billions of Kelvin, they will create, it will, due to this higher temperature, there will be very high or extremely high energy photons. And these photons can break up these heavy elements at the central region. And as a result of that, you will have protons, neutrons, and electrons at the central region of this star, right? And this whole process is what we call as the photodisintegration, right? Right. Now, this is the point that where we have these supernova explosions. Remember that we used this word previously as well, but we did not discuss what is a supernova and how they are created, and these kind of things, right? Now, this is a good point to discuss about supernovas, and especially first I will talk about this type 2 or core collapse supernova, because that will happen as a result of this whole process. Now, when this core continues to collapse of these high mass stars, you will have very high densities at the central region, and the values of these densities will be so high that the electrons and protons, we know this, due to this photodisintegration process, you will have electrons, protons, and neutrons, right? But at the same time, when these electrons and protons squeeze together, they will form neutrons, right? So you will have a lot of neutrons at the end, at this central region, right? And this the core collapsing situation is suddenly halted, so it will stop at a particular point, and that condition is where you have neutrons come into contact with each other. Remember that as a result of this higher temperature, we have this photodisintegration process, which you have electrons, protons, and neutrons. And at the end, then you have a lot of neutrons after this star collapse. Furthermore, you will have a lot of neutrons at the central region. And when the neutrons come into contact with each other, this will make something called neutron degenerate pressure, right? And so that's because you know that neutrons are similar kind of particles, so that once they come into contact with each other, they will make a pressure, right? So that is called neutron degenerate pressure, right? So once the star reach to this particular situation, then it's hard to compress this matter further, right? So then what will happen is, all the materials that is like plunging to this central region due to the gravity will rebound again to the outward direction, right? And this will happen with very high speed. You can see that, just imagine the situation that at the central region you have these millions of kelvins of decrease, and at the same time you will have just neutrons at the central region, and there is high pressure inside that, and due to this huge mass of the star, all the matter is trying to contract towards central region. And when this is halted suddenly due to this neutron degenerate pressure, all the materials that are trying to collapse towards the central region of the star will rebound again towards the outward region, and these rebounds will happen at very high speeds, right? And this particular phenomena has a specific name, or we call that as core bounce, and this will generate very powerful shock waves, which blast away all of the material surrounding the core, right? So basically, you can see that this process is a very, very violent process, and this huge explosion is actually what we called as a core collapse supernova or a type 2 supernova, right? Once again, so if I summarize what I explained up to now, due to this photo disintegration process at the central region of the star, you will have electron, protons, and neutrons, and then when the star further collapses and the density increases, you will have neutrons at the center, and when the collapse happens further, all these neutrons come into contact with each other, which will make something called neutron degenerate pressure. So once you have the neutron degenerate pressure, it's very hard to overcome that by this gravitational collapse, so that all the plunging materials towards the central region of the star will bounce back again with very high speed, right? And this will generate these very powerful shock waves, and this whole process, this once you have these powerful shock waves, they will blast all these materials and around the core, and basically all these materials will be ejected out, right? And this is what we called as core collapse supernova, right? Or type 2 supernova, right? So this is how a supernova is created, especially this type of supernova. Now remember that comparing this particular situation with the white dwarf star, white dwarf star is balanced due to electron degenerate pressure, right? Because it's a low mass, they are low mass stars. Electron degenerate pressure is enough to balance the gravity. But here it goes further step beyond, and then you need neutron degenerate pressure to balance balance these high mass stars, right? And as a result, you will have a very dense core with neutrons, and then you have these bouncing back materials in very high speeds with all these shock waves, which creates a blast, which we also called as a core collapse supernova, right? So that is how a supernova is created, right? Now, actually, there are three names that I will discuss in this particular lecture. One is this type 2 supernova, and then there is another one called novae. Actually, nova is the simple tense of that, and the singular, and the plural word we used to call as novae, not supernova. It should be supernovae. And then there is another process called novae or nova, right? And then there will be another one called type 1 supernova. So I will discuss all these three, but this type 2 supernova is what is directly related to these high mass stars, right? And the next two things that I am going to do next, nova and type 1 supernova, are actually related to low mass stars. Even though I talk it here under high mass stars, the next two processes will be directly related to low mass stars, right? It is just that I need to discuss all these supernova types at the same place, so that is why I put it here. But these are actually as a result of low mass stars, and there will be a white dwarf star involved in these processes, right? Now, this process, which we call as nova, is actually uh, now the previous one, the type 2 supernova is stellar explosion occurred due to high, as a result of this death of high mass stars. But white dwarfs are also a site of explosions, right? Uh, but this process is very different. It's not just involving only a white dwarf star, but it will have another stellar companion nearby. So what will happen is, when you have a white dwarf star and a close by star, so basically there are two stars, right? There will be a white dwarf star and there will be a closer companion, which is not a white dwarf but some kind of a star nearby, right? Then what will happen is, so white dwarf star will try to accrete additional matter from this nearby star. And you know that in a normal star, you will have hydrogen, right? So what will happen is, the white dwarf star will try to accrete matter from this nearby star, and this accreting matter will be mostly hydrogen gas, because you know that most of the material in a star will be hydrogen. Right? So it will try to accrete this hydrogen from a normal nearby star. Now, when enough matter is built up on the surface of a white dwarf, what will happen is, this hydrogen gas will ignite and undergo a thermonuclear fusion. You know that hydrogen is the first one that we discuss in this process that can undergo thermonuclear fusion, right? So same kind of thing will happen here, but this will happen on the surface of the white dwarf, right? Because when you accrete some matter, the normal matter from a companion star, that matter will go into the surface of the white dwarf, right? I will have a picture, like a diagram, that I will show in the next slide. And when this thermonuclear fusion happens in the surface of the white dwarf will be brightened dramatically for few days and then gradually fade away back to a normal situation, right? So this is basically happened due to this accretion of matter from the companion star, and then having a hydrogen fusion at the surface region of the star, right? And this particular process is what we called as a nova, right? And if I show it in a diagram, this is what will happen. So you have a white dwarf star right at the central region here, and here is a normal nearby star. So this is a normal star which has a lot of hydrogen inside that, and due to this gravity, the white dwarf, it will accrete some of this material towards the surface of the white dwarf star, right? So then this material go around on the surface of the star. And once you have enough material, and by the way, this particular outer region we call it as a accretion disk, right? And at the same time, this particular place where you start to get material accreted is called the hotspot, right? So hotspot is where the matter from the normal star meets the accretion disk, and so combining both these stars, we used to call this as a binary system, right? So you will learn probably at the end of this lecture series, when you have two stars uh, together, we used to call them as binary system. So this is one kind of a binary system, right? So there are examples, that observations of these novas, and this is 1935 and 1934, that astronomers have observed this particular nova, which is named as Nova Hercules, right? In the left-hand image, you can see that uh, the brightness has suddenly increased unusually, and then the same star that you can see in the right hand image from these two red arrows, the brightness has decreased after some time. Now this is due to this uh, sudden thermonuclear fusion happens on the surface of the white dwarf due to the material accreted by this nearby normal star, right? So this is an example, right? Now that's one thing that can happen, but if there is a certain condition that if that satisfies in the same process that you have a nova, it can become a supernova. And we call this particular supernova explosions as type 1A supernova, right? Now, what can happen here is if this white dwarf accretes more and more matter from its companion, so there is another extreme scenario that can happen, right? So one thing that can happen is it can become a nova, as we explained in the previous slide, by having all these materials outside the surface of the star, which will lead to uh, thermonuclear fusion and the sudden increase of the brightness. But by having accreting all these materials from this normal star, and if the mass of the white dwarf star exceed this particular mass, which is 1.4 solar mass, right? Then it can no longer supported by this electron pressure. Remember that white dwarf is in this balanced state due to the electron degenerate pressure, right? We discussed this last time. You have the electron degenerate pressure at the center and it will balance the gravitational forces coming from the outside towards the inner region. So that's how a white dwarf is balanced. However, due to this accretion of matter from a nearby star, if the mass of the white dwarf exceeds this particular limit, 1.4 solar mass, then what will happen is this electron pressure will not be able to support the gravitational forces or the gravity, right? And there is a specific name for this particular value that is called Chandrasekhar limit, because he is an actually Indian physicist, and he is the one who discovered this particular process, right? Especially this value 1.4 solar mass, and because of that, it is called Chandrasekhar limit, right? Now, what will happen when the white dwarf's electron degenerate pressure cannot support it? Uh, So then what will happen is the white dwarf will start to collapse again, right? Because now you have more mass. So this mass cannot be supported by electron degenerate pressure. And because of that, the white dwarf will start to collapse. Now, when this happens, the temperature of the central region will increase very rapidly, and this will cause a carbon ignition, right? So you remember that in the white dwarf at the central region, you have carbon. So this is what we discussed last time. Now the carbon will start to ignite due to this violent process because the temperature goes or temperature increases, right? And what will happen is this is not a like a normal process, right? So this happens suddenly by this additional matter coming from this companion star. Because of that, this carbon ignition will happen throughout the entire white dwarf, not like in the previous case, right? Or in the previous case, what will happen is in the central region you will have carbon ignition and make the higher material, and then you will have a shell outside like that. But this is not something like this, because of this material just plunging suddenly into the white dwarf, and when it exceeds this particular mass, the whole star will go through this carbon ignition, right? And because of that, the whole star will explode suddenly. And this process is what we call as the carbon detonation supernova or type 1A supernova. Right? So make sure that you understand the differences between each of these processes. So we had type 2 supernova, which comes as a result of the neutron degenerate pressure holding, imploding, because of the neutron degenerate pressure, when you have this inward materials, they will bounce back and create shock waves, which will lead to this type 2 supernova, right? And then we have a nova, which means a white dwarf, there is a white dwarf star and a nearby normal star, and this white dwarf star will take materials from this nearby star, and once you have enough hydrogen material around the surface of the white dwarf, it will go to just normal thermonuclear fusion on the surface, which will lead to increase the brightness of the star. So that is called a nova. And if this accretion of material exceeds a certain limit, which is the Chandrasekhar mass, then this will lead to ignition of the whole uh, star, right? And once you have this, and this will completely explode the complete star. And this is what we call as the carbon detonation supernova, right? So make sure that you understand the differences between each of these processes. And these numbers I have, it is changed a little bit, right? So I just talk type 2 first and then type 1 like that. Right? Right. Now, why we talk about these supernovas more frequently? Actually, there are different reasons for them. One is actually the supernovas produce enormous amount of higher energies, and other than that, this type 1A supernova, which is the last one that we discussed, which happened due to this process with the Chandrasekhar limit and the white dwarfs, are actually used as distance indicators. What this means is actually we use these type 1 supernovas to measure distances. Now remember that during this course we have learned different methods to measure distances. The number one that we learned is use the parallax method to measure the distances. In that way we were able to measure the distances to nearby stars, right? And then we talk about uh, some other methods to measure the distances. And apart from that, uh, so we basically used the parallax method previously, but at the same time, we actually discussed that this parallax method will not work for distance objects because when you go for higher distances, this parallax angle will become smaller and smaller. The sensitivity of the instruments that we are going to use will not be that much to get accurate values for the parallax angles, right? And because of that, you have to use some other methods to measure these distances. And this supernova use of supernova to measure distances is one of the very efficient methods when you go to make measurements to galaxies. For example, if you need to make the measurement for other galaxies, this is a very accurate and very useful method. And all you need to do is try to locate one of these type 1A supernovas in these galaxies, then you can accurately measure the distance to that particular galaxy. Now, the reason is that, uh, as I have mentioned here, if the distance to a faraway galaxy is required, one must first locate a type 1A supernova in it and then measure its observed brightness. All you need to do is locate the type 1A supernova and then measure the brightness of that particular supernova, right? And then comparing this result with the known maximum achieved by all such supernova, one can determine the distance to that interested galaxy. Now, this is actually because these type 1A supernovas has certain features or characteristics, right? So they have this maximum brightness value, and that will be same for all the supernovas. And this is the advantage actually we have, because when you observe the brightness from a certain supernova, we used that with the curve that we already have, and then you compare those and then you set the distances, right? So that's how you do it. And the other advantage is, since these supernovas are extremely bright, this method is useful to very large distances, because you know that supernovas, as you see, that the amount of the energy that they release is very huge. Because of that, even galaxies that are billions of light years away, still from a telescope, if you have a type 1A supernova, we may be able to detect it, right? Because of that, it's quite possible to measure the brightness and then get an idea about the distance to that particular supernova, right? So once you measure the distance to supernova, if it is inside the particular galaxy, then basically you have measured the distance to that particular galaxy, right? So that's how it works, right? Now let's see whether we have observed any of these supernovas. And as you see here, in our own Milky Way, we have observed supernovas. Now, these supernovas are actually extremely bright, which gives off much light as hundreds of billions of stars, right? So when you have a supernova explosion, it's like the light coming out from that particular explosion will be equal to the light come from, let's say, from billions of stars, right? Because of that, uh, you know that since the brightness is very high, when a supernova occurs in our galaxy, we may be able to visible it, should be able to visible it from the naked eye, which means even without using a telescope, straight away we should be able to see a supernova explosion, right? In our recorded history, we have observed 6 supernovas in our own Milky Way, right? Now, first of these took place in year AD 185, and this event was actually very bright. Even you could see it during the daytime. So that's what the records say, right? And the Crab supernova has occurred in 1054, and its appearance was recorded by these Chinese and Middle Eastern astronomers, and also by the people in North America. And this is also a long time ago. And then most recent supernova is actually observed by Kepler in 1604. So that's the most recent one. And you can see that this event is quite rare, right? In our, if you consider our own solar system, right? And so it seems like it's rare. So let's see whether it's actually rare, right? On average, one supernova explosion occurs somewhere in the Milky Way galaxy every 25 to 100 years. Right? For every 25 to 100 years, uh, there will be one supernova occurs in somewhere in our Milky Way. Right? The interesting thing is actually we have not observed any supernova explosion in our galaxy since the invention of the telescope. You know, the Galileo invented this telescope around 600s, and Kepler has seen a supernova in 604. After that, we have not seen one, right, in our own galaxy. Right? But that's what means here. So the reason maybe we have been maybe exceptionally unlucky, or recent explosions have taken place in the parts of the galaxy where the interstellar dust blocking light from reaching us, right? So there may be two reasons. There may be no supernovas that has happened in past few hundred years in our galaxy, or they have happened in a place where this interstellar dust block the light from reaching us so that we cannot see it, right? So we don't know about. Now, this is actually very a chance event, so that there is no way to say that when the next one might occur, right? It's hard. You know that when you have this Jupiter conjunction and then you have these eclipses, there are news in the, and you will know it beforehand, like this will happen in this particular day. But for the supernovas, it's not the case, right? So it's a chance event that you have to observe the sky, expecting that one day somehow you will see one of these supernovas, right? Now, this is that's about the supernovas within our galaxy, but there are supernovas actually that we have observed very recent, but these are not in our galaxy. Mm. Now, this is one of the supernovas that we have observed, and this image is from the supernova 1987A. As the name suggests, this was observed in 1987 for the first time, and this image is through the Hubble Space Telescope. Just look at this particular image when you have the presentation. So that's the supernova remnant, uh, and this is actually from the Large Magellanic Cloud, and this has observed few times, like in different years. The Large Magellanic Cloud is one of these nearby galaxies for us, right? So it's not our galaxy, and this is a type 2 supernova, which means type 2 supernova is what uh, comes as a result of high mass stars, right? Not low mass stars. And also, this is not a supernova that we use to measure distances, right? Measuring distances is done using type 1A supernova, right? That involves white dwarf and a companion star, right? Make sure that you don't get, like, these names look similar, but they have different processes, right? Now, this is by far the nearest and brightest supernova that we have seen in modern times. Now, how many years this is ago? I guess 1987, so around 33 years, right? Now, just keep in mind that in one day in your lifetime, if you happen to have a supernova in our own galaxy, this will, like, make news headlines, right? So it's rare. Earlier in the photos of the Large Magellanic Cloud showed that the supernova progenitor was a blue supergiant star. So that's basically so where it is originated, uh, and you can actually see supernova remnants. What is remaining after the supernova, even after the, the supernova explosion. Now, this is about the supernova 1987A. So astronomers actually make the life story for this 1987A supernova by combining the theory and observations that we have up to now, and this kind of nicely summarize the whole process, what will happen to a star from the beginning. And this is the prediction for this 1987 supernova, what has happened to it from the beginning, and different parameters, right? And you can see that it starts from the hydrogen fusion, and then it goes to helium fusion, carbon fusion, and this is, by the way, a high mass star. That's why you have a type 2 supernova, and neon, oxygen, and silicon fusion, and then you have the core collapse. And it is interesting to note the temperature increase from hydrogen fusion up to the core collapse, and the density increase, and the time it takes for these different phases, right? It is the hydrogen fusion that took a long time, and then after that, for each phase, it spent only smaller time, right, compared to the previous one. And you can see that from the silicon fusion, it only has spent like few days, right? Now we don't know what when we will see the next supernova in our Milky Way, maybe tomorrow and maybe after 100 years. So just keep that in mind. Now this is a very recent supernova that we have observed. Remember that what I am telling here is the supernovas outside our galaxy, right? Not inside. Inside our galaxy, we have not seen one after 604. And this is called supernova 2014J. And this image of the supernova is located in the Messier 82. Messier is like a kind of object, and also known as the Cigar galaxy, right? So this Messier object is actually, this name came from this history that you have something called Messier catalog, that people have cataloged these what we call these extended objects without knowing that they are galaxies. So we are using the same names till now. But M82 is now identified as a galaxy and named as the Cigar galaxy, right? And this is a Hubble Space Telescope, and the small white window enlarged here in the picture is where you can see this supernova. And this is, by the way, a type 1a supernova, right? And which is theorized to be triggered in the binary systems consisting of a white dwarf and another star, right? So this is an example of a type 1a supernova which involves a white dwarf star and another star, right? And this star is very similar to our sun, by the way, because our sun will become a white dwarf one day, right? So something that can happen to our sun is after 5 billion years, it will become a white dwarf and then go into the white dwarf phase. And then if it has a companion star nearby, it will become a type 1a supernova, right? It can happen, right? So make sure that you understand these relations. So that's what that those are the things that you have to understand. Like for example, if I ask from you, uh, is it possible for sun to become a type 2 supernova in after few billion years? Then what should be your answer? Is it something that can happen? Anybody would like to answer? It cannot happen, right? Because our sun has just one solar mass, and this particular our sun is a low mass star, and it will become a white dwarf one day. So if it becomes a white dwarf, the only possibility that has is if it has a nearby star, then it can become a nova or type 1a supernova, right? It cannot be a type 2 supernova, right? Because for a type 2 supernova, you have to have a huge mass, right? So that is only applicable for these high mass stars, right? And the distance for this particular supernova has measured, because once you detect a type 1a supernova, you are basically done with the distance. You can measure the distance accurately, and that distance is approximately 11.5 million light years from the Earth, right? You can see that this is not in our galaxy, this is far away from us. And this is, by the way, the closest supernova of type 1a discovered in the past few decades, right? So this is the closest one we have for the past few decades, right? So let's see how whether we have detected any supernovas in distant galaxies. With modern telescopes and detectors, now it is possible to detect supernovas in very galaxies that are distance away, right? Thousands of distant supernovas have now been detected, and many of these are billions of light years away. The previous one that we talked is actually, even though it's like 11.5 million light years away, compared to the scale of the universe, it is still a close by one, right? And So once you have a supernova, actually the supernova will be bright, very bright compared to its own galaxy, right? So it can even overcome the brightness of the galaxy, right? And we have detected both carbon detonation of the type 1A and type 2 supernovas, but these are very far away. Now, on average, both types of supernovas are estimated to occur approximately once every 40 years per galaxy, right? So that is the estimation of astronomers depending on the data that we have, data and the theories that we have, right? And then uh, we we actually have supernova remnants, by the way. So the supernova remnants means the remainings after you have a supernova, right? Supernova, these are extremely bright phenomena, and then but they only last for few months. So if you miss it, then you miss it, right? But uh, we are fortunate that once you have a supernova, they will leave some remnants which are relatively faint, right? Now, these debris from a supernova, including heavy elements, these can be observed for hundreds or thousands of years later, right? So even though supernovas are rare and at the same time they last for only few months, after the supernova explosion, the debris from the supernova explosion can be observed for thousands of years. Even after 1,000 years, you can observe those, right? Now, this Crab Nebula is actually something like that. So that's a remnant from the Crab supernova, which has happened around 1,000 years ago, right? This Crab Nebula can be seen even from a smaller telescope, right? And there are many other supernovas actually that you can see like that in our galaxy, right? Now, these are like two examples like that. The two supernova remnants. The first one is the Crab Nebula that I have explained in the previous slide. And the second one is called supernova 1006 remnant, again observed from the Chandra X-ray Observatory. Right, so that's the end of that section about, I would say, the story of these high mass stars. Now, if I summarize that particular section, so what we discussed is starting from high mass stars, we discussed uh, what happened to these nuclear fusion reactions. So they will not like the low mass stars, since these fusion reactions involved in heavy mass stars, they can make heavy metals at the central region, and then they will create these onion skin type of shells or layers of material starting from iron at the center. All the materials will have shell structure inside that. However, when the so there will be a point that you have this heaviest material, which is iron. So iron cannot be fused anymore. Because of that, the reactions will stop at that particular time, and then you have this gravitational collapse towards the inside. And when the temperature increases due to this process, and when the temperature go up to these millions of Kelvin, this process we discussed as the photodisintegration will happen at the center, which will lead to electron, proton, and neutrons, which will create electron, protons, and neutrons at the central region of these high mass stars. And then when you have further gravitational collapse, all these uh, electrons and protons will squeeze together, and at the end you will have a lot of neutrons at the center. And finally, when neutrons come into contact with each other, they will create something called neutron degenerate pressure, And then it is hard to overcome this neutron beam rate pressure by the gravitational forces, and because of that all these materials plunging inward will be bounced back again very high speed by creating these shock waves, which is a very violent process, and this will lead to this type 2 supernova explosion, right? So that's what will happen to a high mass system. And at the same time we discuss these other two types of supernova explosions, type 1A supernova, which comes as a result of this low mass stars, which is a white dwarf having a companion star and accreting matter, and have the final mass of the star going beyond the Chandrasekhar, right? So this will completely ignite the carbon inside the star and explode it, right? And there is something that can happen before that. If the mass does not exceed the Chandrasekhar limit, then that particular star will become a nova, right? And then we discuss about the observations of supernova and those kind of things. So that is kind of the summary which we had for this section, right? Now I
Sir,
am
sorry, sir, we can't see anything, sir.
sorry.
We can't see anything, sir. Only error message we can see.
You say you are telling that you can't see anything. I'm just only thing that because I have not shared anything with you, right, at this particular point.
Okay, sir.
What I am doing is I am just explaining or summarizing what I did up to now for today's lecture, right? Now, let me, right, before I go into next section, so the next section is again actually related to these high mass stars, but that's a different section that we will discuss what happens after these supernova explosions for a star, right? So this will be about basically about neutron stars and black holes, which will I will take some time to explain, and this will also involve some of these cosmological theories such as basic introduction to general relativity. Especially when we talk about black holes, we have to just discuss about that. And before I move into that section, uh, if any of you have any questions, please feel free to ask. Right? Otherwise, I will take probably another 15 or 20 minutes. Just we'll try to go through a little bit of the next lecture series. Right. So while I am pulling up my next presentation, you can ask any questions if you have. Right. So if you do not have any questions, so I have started sharing the next section in the lecture, which is about these neutron stars and black holes. Right. So I now actually I am sharing my presentation. Now, if you cannot see it, then please let me know in case if you can't see my presentation. Right. I have shared my next section, which is about neutron stars and black holes. Right. Uh, you will see that this is again a continuation of what we have been discussing, right? So this is like a story now. This what happened to these stars at different, based on their initial properties at different stages, right? Right. So let's start talking about this neutron stars and black holes. So once again, I will start from where we had this type 2 supernova, right? Now, during this carbon detonation supernova, which we also call as the type 2 supernova, we told that, sorry, so I just made the mistake here. During the carbon detonation supernova, which is the type 1A supernova that involves a white dwarf and a companion star, the entire star explodes, right? So there will be nothing behind, right? However, for these high mass stars, when you have this type 2 supernova, this will actually explode. You will have an explosion, but that explosion leave a dense core after that, right? Remember, this type 2 supernova happens once you have all these neutrons squeezed together at the central region, and then the material coming towards the central region will be bounced back, right? So those are the materials that will be ejected away in a type 2 supernova explosion, so that still you will have this dense core at the central region even after the supernova explosion, right? Now this tiny core that is remaining is actually basically that consists of these compressed neutrons. So basically you will have neutrons in that core, and this is actually what we called as the neutron star, right? Basically the remaining dense core after this type 2 supernova explosion is what we called as the neutron star, right? So you may have heard these words before, but this is what actually it means, right? Now, what do you think about the density of a neutron star? Actually, these neutron stars are extremely dense, and if I give you an example, so these are typically about 20 kilometers in diameter, right? So just think about, like, these are small objects, but we used to tell that these are 20 kilometers in diameter, right? In astronomical scale, these are small objects, right? And the interesting thing here is its diameter is 20 kilometers, but this will be more massive than the sun, right? So think about that situation. Then you can think how dense are these objects. And if you compare the density with the white dwarfs, uh, the neutron stars are actually billion times denser than the white dwarf, right? And if you consider about our Earth, neutron stars are actually 10 trillion times denser than the Earth, right? So that is why these objects are like so special, and that is why we are actually talking about these specifically. And the other properties of neutron stars are they are extremely small, very faint, and because of that, what happens? Hard to detect, right? If there is something, even though they are very special objects, if they are faint, because you know that it's only contain these neutrons, right? So there is no way that it can power up. So there is no way that it is, you will not be able to see those easily, neutron stars. Now, while their existence has been predicted, they were thought to be almost undetectable because they are very faint and we don't know a way of detecting those, right? Because they are faint objects, right? But however, in 1967, astronomers who use a radio telescope, they detected an object that was giving these rapid pulses of radio waves. They actually did not know that it is a neutron star, but they have detected an object that gives off rapid radio pulses. And now the these pulses actually detected once every this much of seconds. So this you don't have to remember these numbers, but you can see that they are very rapid pulses, right? Every 1.33 seconds there was a pulse in radio wavelength, right? So this is not in visible wavelength. And once you have a pulse, it lasted only for about 0.01 seconds. So very small time there was a pulse and then it goes away and then it comes again like that in radio wavelengths, right? So that pulses looks like something like this. So you have a pulse and then it goes down for some time and then again you have a pulse like that, right? So this is what I mean, right? And These are actually called as pulsars later, right? So you may have heard this name pulsars. So that is why you called it as a pulsar. So these objects are called as pulsars. So initially they appear to be found in blank places on the sky, right? Because you just have pulsars. However, there was one actually found right at the heart of the Crab Nebula. I remember the Crab Nebula is one of the supernova remnants that we discussed in the previous lecture, and there was one of these pulsars that astronomers has found right at this heart of the Crab Nebula, right? Now we know that these neutron stars are actually pulsars because it was in the Crab Nebula, and this should, you know that when you have the Crab Nebula, that means there should be that is a site for supernova explosion, and after the supernova explosion there should be a neutron star here, right? And this neutron star should be the one that actually emit these pulsars, right? So that is why these pulsars are connected in the neutron star, right? And we now know that the neutron stars actually have very strong magnetic fields, and these magnetic fields actually can accelerate charged particles from their magnetic poles, right? And these accelerated charged particles uh, is responsible for this emission of radio waves, right? So that's what has happened. So basically, there is a connection between neutron stars and pulsars, right? So that's what I want to mention here, right? So this basically explains the same information, and other than that, these neutron stars actually rotate very rapidly, and this is why astronomers have first detected these rapid radio pulses, because the neutron stars has this magnetic pole which lead to these radio pulses, and at the same time neutron star rotates rapidly, so that you just have these pulses uh, in a periodic manner, right? But there are some things that you should note here. These magnetic poles of neutron stars are not aligned with the rotation axis, right? Neutron stars are actually rotating around an axis, but that axis and the magnetic poles are actually not aligned with each other. You will see it in the next picture. So what actually happens is when the neutron star rotates, its magnetic poles may point towards us, right? Depending on the orientation of its rotation, magnetic poles may point toward us, and that may be the reason that we get these pulsars from neutron stars, right? Now here is a picture that shows it, and you can see that in this particular picture, the axis of rotation of the neutron star is somewhere here, right? So you can see that this is the axis of rotation, but the magnetic field is in this direction, right? So if the orientation, if our Earth is, let's say our Earth is somewhere here, not actually here, if we will be in this path, then you will detect these pulsars, right? But it's a chance thing again. I mean, if we are, if this is oriented in a different way, there may be a neutron star, but we may not detect pulsars, right? That's how it works. And here is a model of a pulsar, the diagram that showing how beams of radiation. Now you can see that again. Here is the rotation axis, and then with the rotation axis, you have a neutron star right here. There are beam of particles and radiation that goes around these two regions, and then you have the magnetic poles, and here is the Earth right here, and you can see that when this rotates around this rotation axis, there will be some point at a certain point, this beam of particles will sweep through the earth, right? So this is the time where you will get pulses, right, or pulsars. So that's what will happen, right? Now here are some properties of actually a white dwarf and a neutron star. And remember that the reason that we talk about pulsars and neutron stars both here, the actually pulsar is actually a rotating neutron star, right? So that's what has happened. But the converse is not true. There may be neutron stars that are not pulsars, right? That can happen. But all these pulsars should be a neutron star. So that's what we know. And from here you can see that the white dwarfs has zero point 0.6 mass, and a neutron star is greater than 1.4, which is a Chandrasekhar limit, less than 3 solar masses. By the way, these are solar mass in terms of the units, right? The radius of a white dwarf is 7,000 kilometers, while the neutron star has just 10 kilometers, right? And density is huge in the neutron star. So this is just a comparison again of different properties of a white dwarf and a neutron star. Now, the next question is, which I have just mentioned, whether all neutron stars are pulsars, right? Now, according to the models that we have, there are rapidly rotating neutron star. Uh, the model of the rapidly rotating neutron star can explain this pulsar phenomena, right? So remember that we had this model right here. This is a neutron star with the magnetic field. When it is rapidly rotating, you will detect pulsars, right? So which means that particular model tells you rapidly rotating neutron star can be taken as a pulsar, right? For a given neutron star, we will not detect as a pulsar unless its magnetic pole happen to point towards us during its rotation, right? Remember, this is a requirement. I mean, you can have a neutron star uh, rotating, but we will not detect it as a pulsar if its magnetic pole happens to point towards us, because the magnetic pole can be directed towards another direction. No? Not, it doesn't need to be, it doesn't have to be in our direction, right? It's a random thing. Sometimes it direct towards the earth direction. So in addition, the pulsar phenomena dies off after few 10 of million years, right? Which means you will see in the next particular slide that what will happen is, once you have this rapidly rotating stars at the heart of one of these nebulas, these rotational energies will be taken by the surrounding material to energize those materials. So once you have this, you know that according to basic physics, once you consume energy for something, your energy will be lost. Right? The same thing will happen to these pulsars. Their rotational speed will decrease little by little uh, due to this phenomena, and we will see it in the next slide probably. And so this, which means these pulsars phenomena will slow down little by little, and also its magnetic field weakens with time, and therefore all pulsars are thought to be neutron stars, but the converse is not true. So make sure that you understand it, right? If you see a pulsar, you can definitely tell that it should be a neutron star, right? All pulsars are thought to be neutron stars. But that does not mean that all neutron stars are pulsars, right? Once again, if you will detect a neutron star as a pulsar only if that particular magnetic field is directed towards to us, and also it has to rotate. Neutron star has to rotate rapidly, right? Both of these conditions has to be satisfied for neutron star to detect as a pulsar, which means all the pulsars you detect should be a neutron star. But there can be neutron stars that you cannot detect as pulsars. Right? That's why I have mentioned that the converse is not true. Right? Now this is what happens after a long time because of the rotational energy will be used to excite. Now this is an example of the Crab nebula, right? Now Crab nebula is so this has a rotational energy that will excite the Crab nebula year after year. And what will happen is when it excites the nebula, surrounding nebula, that its energy will gradually and go away, right? Energy will be decreased. Because of that, the pulsar will slow down. That rotational speed will be decreased, right? And this is an example right here. The the pulsar you have in this Crab nebula, uh, when the age is 10,000 years, the period of the pulsar is 30 times per second. So every second it has rotated 30 times. But when the age has become to 10,000 years, once the time goes on, its energy is reduced because the energy is used to excite the Crab nebula. Then its period has reduced as well. Now it's only 11 times per 1 second, right? So that's what will happen to pulsar with the time, right? Now actually that is the primary way of detecting neutron stars. The other methods of detecting neutron stars are actually the radio pulsar phenomena provide the simplest method of detecting some neutron stars, right? The method that we discussed up to now is one of the simple way of detecting neutron stars. However, there are other ways of detecting these same neutron stars because this pulsar phenomena is also seen at other wavelengths, including visible lights. Right? As an example, this Crab nebula has a neutron star at the center, and and also there are some images came from the Hubble Space Telescope that it has detected some of these faint neutron stars. You know that the technology is developing. You can use to get more and more high-tech cameras and large telescopes that you can look at these faint objects, which means the probability of detecting these neutron stars even through the visible light is higher now, right? Now, this is another situation that you have situation that an ordinary star share a system with a neutron star, right? So this is some more information about neutron star. The one in the image in the left hand side, you have a neutron star right here, and you can see that it's rotating. And what happens is there is an ordinary star nearby. So that ordinary star, I mean, this is not a common situation because the neutron star usually comes as a result of this type 2 supernova explosion, right? Because of that, it is not always that you have a nearby star after that, but there are situations that you may have something like this, an ordinary star nearby. Then this gas from the ordinary star can be accreted towards the neutron star, right? The materials will be transferred from this living ordinary star to this dead companion. Dead companion means a neutron star, right? We used to tell that a neutron star is a dead star because it doesn't go through these nuclear fusion reactions. Now, what can happen is this infalling due to this infalling gas from the ordinary star. So this gas will be compressed and can be heated to very high temperatures. So when the gas is heated to very high temperatures, this will quickly become hot, uh, and then you will have explosive burst there, right? So this will lead to This will actually emit X-rays. Now you can see that the beam of X-rays moving out to this direction and that direction. And this is another way of detecting neutron stars, looking at these X-rays from X-ray telescopes. Right? So I'm basically explaining that apart from this having a pulsar as a radio in radio waves, the other ways of detecting these neutron stars, right? And this is an example of this looking at the pulsars from other wavelengths, which I have explained. Right, so I guess the sign time is close to 7:30 already. So if anybody, so I am going to stop. Let me see. Yes, so we will, yeah, just go. We will started to talk about black holes next day. I will upload this presentation up to here, and yes, the last few images are just some of the examples of the detection of the neutron stars, so that you can just read through. And after that, this starting from this mystery gamma ray slide, I will be talking about black holes, right, in the next day, and plus general some of the basic concepts in the general relativity. Right. So to stop with for the final few minutes, anybody have any questions? Feel free to ask. If not, we will stop, and I will try to have schedule another lecture on Saturday for the same time. But I will update you about that probably tomorrow or Saturday morning.